Hello everybody. In this video we're going to introduce one of the more important topics, at least if you actually want to know, say, what the real numbers actually are. And that's the topic of Cauchy sequences. I'm going to introduce it in a slightly unconventional way, but if you've never seen it before, well then you won't know that. So I want to start by writing down a new definition. Not of Cauchy sequences yet. We're going to build towards that. Instead, I want to write down what I'm going to call a 2D sequence. So recall that, right, a sequence, all right, what was that? This was a function, whose domain was the set of positive integers. Okay, codomain is, well, whatever the values of the sequence are. That's all sequence was a function whose domain is the positive integers. What I would like to do is to write down a version of a sequence that takes not one positive integer as an input, but rather two positive integers as an input. So the way I'll do that is by defining, not the, but a 2D sequence. So it's going to be called a 2D sequence. So think, when you think 2D, think like 3D, right? Dimensional. So a 2D sequence is a function with domain. Well, again, I want two copies of positive integers in here. So I'm going to use the Cartesian product. Okay, so everything in here is going to look like some m comma n, where each of m and n is a positive integer. Right? And of course, since we're in a real analysis class, the codomain is just going to be the real numbers for this 2D sequence. Okay, notationally, since I need to put in two inputs, right? I need a first component and second component. My notation for such a 2D sequence will be an A with two dots, right? And okay, I guess you could imagine me doing a 3D sequence with three dots, but of course at some point it starts to look pretty funny. Alternatively, we might write it down using this parenthetical notation. So I'll write A, I, J, and here I and J say are greater than or equal to 1. Now, for a sequence, it was fairly easy to, if you like, visualize it. We would just have something like A1, A2, A3, and so forth, right? It all kind of fills up a nice line. With a 2D sequence, we really want it to fill up, well, like a plane, right? We need it to be two-dimensional. So let's take a look at what we're thinking about here. So for my A double dot, then on the side, I might look at the A1 row. Okay, and so that'll be A1J. So you have A11, A12, A13, etc. And then I'd have an A2 row, right? So I'd have A2J, right? So A21, A22, A23. And of course, along the top, I might have my first column. So it'd be AI1. So A11, A21, A31, etc. Now, inside this, you'll notice I've kind of partitioned this up. And that's because for sequences, we usually didn't care about the entire sequence as we cared about the tail. So if I cut off the sequence, say after the third component, then everything afterwards was the tail of the sequence. And we want to have that same notion for 2D sequences since, well, tails is really where it's at. Now, I could assume that for a tail, I just cut off maybe at some point over here, like the fourth, and then the third over here. But for technical reasons, I'm going to assume my tails are always done in sort of a square fashion. So here I'm cutting off after the third row, and I'm cutting off after the third column. So a 2D tail, although we often will just say tail. So a 2D tail of A double dot, right, is going to be essentially this 2D subsequence in the bottom right corner. All right, is the 2D subsequence where I'm going to take A, I, J, but now I and J, I can start it at some later point, like an M, okay, for some positive integer M. Okay, so the tail is just this bottom right corner, right? And of course, I could go out further and have a bottom right corner that starts, even further down, right? And that would be my new tail if I started at 4 or after 4. Okay, now, once again, if I have some real number L, then I can say that this 2D tail is contained in an L coin. Okay, so remember that looks like L minus epsilon, L plus epsilon, if the L coin contains all of the terms in the tail. Right, so if L minus epsilon, L plus epsilon contains all terms in the tail. Okay, and just like for a sequence, we will call these numbers in the 2D sequence terms, right, rather than elements. Okay, so that's a 2D sequence. Now, if I start with a sequence, I can actually define immediately another 2D sequence. And the way I want to do that is a special thing called the 2D difference, right? So another definition here. In fact, we can do this with just any two sequences. So for sequences A and B, the 2D difference. Okay, so remember, you can compute the difference of two sequences by just component-wise subtracting them. Can't spell difference today. Okay. We can subtract, right? So on the side here, right, if I do A minus B, this is the sequence A1 minus B1, A2 minus B2, etc. What I want, though, is a difference, which is actually going to give me, again, this table. And the way I'm going to do that is not by subtracting just each component, right? So A1 with B1 and A2 with B2, but every component of A with every component of B. So the 2D difference is the 2D sequence, which I'm going to denote by, well, I can't use minus because that's already used for differences of sequences. So I'm going to put a circle around it. Okay, and this has some very mild connection with something called a tensor product, but don't you worry about that. All right, and so what is the sequence? It's the one that looks like AI minus BJ, where we let I and J be greater than or equal to 1. So I and J move independently of each other. So things in here could look like A3 minus B5 or A100 minus B2, right? I just get all possible differences of elements from A and elements of B. Now, as I said, I'm going to be much more interested in the case, at least for now, where instead of taking A and B, I'm just taking A and A. So I actually want to be able to compute the 2D difference of a sequence and itself. Okay, so here's an example. All right, we want to do the 2D difference. So I get the circle here. And what is this going to look like? All right, well, so let's bring a picture for this in. Okay, so here I just have A1, A2. I'll just denote my sequence terms on the left here, my same sequence on the top. And of course, you can see here now A1 minus A1. Of course, this is going to be a 0. All right, and then we have A1 minus A2 and A1 minus A3. And over here we'll have A3 minus A1 and A3 minus A2, and so forth. And maybe I look at a tail. All right, and just ignore this for the moment. I look at a tail of this 2D difference. Okay, so that's going to give me all the differences between elements of A past a certain point. And what Cauchy realized is that if we started with some sequence, like A, and we wanted to check whether or not A converges, but we have no idea to what A should converge. Okay, so normally when we test convergence of a sequence, we say, oh, we think it converges to some L, and so we show that every L coin contains a tail of A. But what if we don't know what L is? That's the key. And so Cauchy said, if we don't know what L is, why don't we, instead of trying to get the sequence A to be closer to some limiting value, why don't we check A against itself? That's where this 2D difference comes in, and see if the terms get closer to each other. Now, what does it mean if the terms are getting closer to each other? Then it means that their differences are getting closer to 0. So this is going to motivate our definition of a Cauchy sequence. So a sequence A is Cauchy, or is a Cauchy sequence, if every, okay, and here's where this picture comes in, 0 coin. Okay, so remember, we're trying to get the tail of this 2D sequence to get closer to 0, meaning we want the terms to get closer to 0, which means we want them to be inside of a 0 coin. You give me some epsilon, I go out, pick a tail so that all of the terms in the tail lie within that 0 coin of radius epsilon. So a sequence is Cauchy if every 0 coin contains a tail, not of A, but of this 2D difference of A with itself. Okay, just meaning, go to this picture, look at the right-hand corner. Are all of the differences that you get, and heck, some of these are 0, right? On the diagonal, they're always 0. But some of them may not be 0, and do they at least lie in the 0 coin of radius epsilon that you've written down? And if somebody picks a new epsilon, maybe you have to pick a new tail. Okay, so that's our definition for a Cauchy sequence. Now, it's going to turn out that Cauchy sequences are always convergent sequences and vice versa. So this actually could have been the original definition of convergence. We're going to write that down as a theorem in a moment. First, I want to write down sort of an intermediate step. This will actually, we're not going to prove what's called the Cauchy Criterion in this video, but we're going to use this next theorem when we do eventually prove it. So this theorem is that Cauchy sequences are bounded. Okay, and I'm not even going to write down an explicit definition or an explicit statement of this theorem because it's right there, right? I would say every Cauchy sequence is bounded. That's the theorem. So let's do a proof. So let's say I have a Cauchy sequence, right? So let A be a Cauchy sequence. So I know that every 0 coin contains a tail of the 2D difference of A with itself. Fine. If it works for every 0 coin, then certainly it works for the 0 coin of radius 1. Okay. So the 0 coin -1, 1 contains all elements of the form AI minus AJ. Okay, so this is what things in the 2D difference look like, at least for I and J large enough, right? So I and J greater than or equal to some positive integer n. Okay, so this is, right, telling you the tail. Okay, so if my AI and AJ are coming, AI minus AJ is coming from the tail of the sequence, then we know that it's going to be contained in -1 to 1. Okay, but let's say then I choose some little n, at least this big N. Right? So I might have this sequence, and we'll just write it like this: A1, A2, A3, A4, and it keeps going, and at some point I get to AN. And then I keep going some more, right? Oh, I have an AN plus 1 and dot, 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 dot. And at some point, maybe I get to this A little n. And I'd like to know how far away the values of a little n and the values of a n are. Right? But here's what I know. I know that if I subtract a big N from a little n, because they are both, these indices, little n and big N, are both greater than or equal to n, meaning we're in the tail, right? So there's a sort of a tail starting, which we're projecting now. So we're in the tail. That means that this difference lies in the zero coin, -1 to 1, okay? Because that's what we said. The zero coin, -1 to 1, contains all elements of this form as long as we're in the tail. Heck, we're in the tail. Okay, but if I want the distance, then I need to take the absolute value. And if the difference is between -1 and 1, then the absolute value is less than 1. So this tells us that a little n and a big N are less than 1 apart. Okay, so they're somewhere on the real number line. We have no idea where they are, but when we find one of them, the other one can't be more than 1 away. Now, if we take absolute values of those numbers, that still has to be true, right? The absolute values still have to be 1 away. So the absolute value of an and the absolute value of a big N are less than 1 apart. And so what that tells us is that the absolute value of little n is bounded by the absolute value of big N plus 1. Okay, it cannot be any bigger or even as big as this number. Okay, but this number here is fixed. Right? This is just some single n. Little n, that could be anything bigger than big N. Okay? But this is some fixed number. Take the absolute value, add 1, just some number. And what this shows is that in the sequence A, once you get past big N, all of the terms are bounded by this fixed number. So we know that this tail, all right, therefore, if we look at the sequence A greater than or equal to N, right, this is a tail, is bounded. And it's bounded by absolute value of A big N plus 1. Okay, well, does that mean that A is bounded by the same number? Not quite, because we've only dealt with this tail. There's also the head. However, unlike the tail, which is infinite, the head is finite in length. And any finite set has a maximum. So the set A1, A2, ... and what's the last one right before we get to AN? That'll be AN minus 1. So that's the last bit. This set is finite and hence has a maximum. Okay, of course, if you have a maximum, then you're bounded. And so I don't know if that maximum is bigger or smaller than this particular number here. Maybe this number is like, I don't know, maybe 18. And maybe the max over here, right? Maybe there's some element equal to 1,000,000. In which case, okay, this 18 is no longer relevant as a bound for A. The million is the relevant number, but we don't care how big that number is, right? We just want to know that there is a bound. Okay. And by the way, like even if we replace the A1 through AN minus 1 with the absolute value versions, then that's still going to be bounded, right? And so between the two of these, right, so we now know that the head is bounded, and we know that the tail is bounded, and so the whole sequence is just going to be bounded by whichever is the max bound, right? So take the max bound. Okay, thus A is bounded. Okay, so that finishes the proof. Okay, so we're going to finish this video by writing down a theorem, which again, we're not going to prove it right now, but this is a very important theorem for us, which is called the Cauchy Criterion for sequences. There's also going to be one for series, although it really won't say anything new. And it simply says that a sequence converges if and only if it is a Cauchy sequence. Okay, and so when we do prove this, we're going to throw a whole bunch of things together, including things like the Bolzano-Weierstrass theorem. Okay, that's going to be very important. The other thing I'll tell you is we're going to, in the second half of this class, do something called the construction of the real numbers. And these Cauchy sequences are going to be instrumental in us doing that. All right, so the idea is you're going to start maybe with the rational numbers and say something like, oh, look, 3 is a rational number, and 3.1 is a rational number, and 3.14, and 3.141, and 3.1415, and 3.14159, and so forth. I keep on adding one digit. And if you, are good into your trivia, you'll know this, not funny arrow, straight arrow converges to pi. But you'll notice these are all rational numbers, and it's converging to something irrational. And so Cauchy sequences, and this is an example of a Cauchy sequence, because if we want to get everything, say, within 0.1 of itself, we can just go out far enough, and everything going forward will be within 0.1. Okay, so this is going to be a Cauchy sequence. And Cauchy sequences now say, if you just started with the rational numbers, if that was your whole world, you aren't going to be able to always write down the limit of a Cauchy sequence of rational numbers, because pi is irrational. This is not an element of the rationals. And so Cauchy sequences are going to give us a way of naturally necessitating the existence of irrational numbers, and hence all the real numbers. There's going to be a lot more technical details. We're not going to go into that here. We'll see you next time when we're going to jump into a discussion of infinite series.